On this week, sunspot region AR4436, a magnetically stressed cluster of dark roiling plasma sitting on the northeastern limb of the sun, released an M5.7 solar flare so energetically concentrated that within minutes it ionized the upper layers of Earth's atmosphere over the Atlantic Ocean, wiping out high frequency radio communications across thousands of miles of open ocean. NOAA's Space Weather Prediction Center classified the disruption as an R to moderate radio blackout. Transatlantic pilots lost communications. Mariners navigating open ocean lost their frequencies. The flare also produced a Type 2 radio sweep confirming that a coronal mass ejection had been launched from the solar surface at an estimated initial shock speed of 650 kilometers per second, and as of this moment, May 13, 2026, the outer edge of that ejected plasma cloud is arriving at Earth. It may already have begun its glancing blow against our magnetosphere. Whether the B's component of that incoming magnetic field turns southward, a single directional variable no larger in concept than the flip of a coin, will determine how hard this planet is about to be hit. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources: NOAA's Space Weather Prediction Center, the GOES-19 satellite, the UK Met Office, NASA's Solar Dynamics Observatory, the SOHO spacecraft's LASCO coronagraph imagery, the CN-LIL solar wind model, and peer-reviewed research published in Space Weather Journal, but official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed, the data is public, the responsibility to check belongs to all of us, but that is not even the complete picture, because what is arriving at Earth's magnetosphere this morning is not simply one rogue cloud of solar plasma that wandered into an unfortunate trajectory. What is arriving is the latest signal in a sequence that began accumulating in January, that continued evolving through April, and that is now concentrating its energy into a critical window measured not in months but in days. Sunspot regions AR4436 and AR4432 are both still active. Both are still evolving. Both are developing what solar physicists call gamma-delta magnetic configurations, the most explosive, most unstable geometries that exist on the solar surface. NOAA's forecasters have placed the probability of further M-class flares from these regions at 40% for today alone. The probability of an isolated X-class flare, the most powerful category the classification system recognizes, a level that represents a tenfold increase over what was already recorded on May 10th, is now 10%, and here is where this account becomes genuinely significant. AR4436 is rotating. It is rotating toward what space weather forecasters call the sun strike zone, the direct Earth-facing position on the solar disk where a flare of any significant magnitude would not deliver a glancing blow. It would deliver a direct hit. What the official data actually shows is a solar system in the precise geometry of escalation. To understand what that escalation means, to truly feel the weight of what the instruments are showing, you must understand what a coronal mass ejection actually is at the scale that reality demands. The sun launches these events at rates that vary with its 11-year cycle, near solar minimum, perhaps 2 per day, near solar maximum, which solar cycle 25 reached roughly in mid-2025 and is sustaining into 2026 as many as 3 to 5 per day. But the vast majority travel outward into the void, missing Earth entirely. Only the ones aimed directly at our small blue target matter, and what determines whether any of them cause catastrophe is a single property: the orientation of the magnetic field frozen inside the plasma cloud, if that field points northward when it arrives. Earth's own northward magnetic field largely deflects it. The door stays closed. If it points southward Bs, as forecasters call it, then magnetic reconnection occurs at the boundary of our magnetosphere, the protective bubble that makes life on this planet possible, and energy pours through like water through a breach. The difference between a near-miss and a civilization-scale event is not measured in size or velocity or temperature, it is measured in direction. A direction that cannot be reliably predicted until the plasma cloud is approximately 15 to 60 minutes from Earth, and at the speed of an average CME shock front, 15 minutes is not a planning horizon, it is a notification. The CME launched by AR4436's M5.7 flare on May 10th carried an initial shock speed estimated by NOAA's Type 2 radio sweep data at 650 kilometers per second. For comparison, the background solar wind blows at roughly 400 to 500 kilometers per second. This ejecta was faster. The CN-LIL modeling run by NOAA's Space Weather Prediction Center, the same model that predicted this arriving at Earth early on May 13th, showed the bulk of the material aimed well east of Earth's orbital position. But the outer edge, the wing of the expanding plasma cloud, is brushing past our planet. That is what a glancing blow means in the language of space weather. Not a miss, not a direct hit, but a graze. And in that graze, enough energy exists to push the KP index, the Planetary Geomagnetic Disturbance Index, to level 5, which means G1, the lowest category of geomagnetic storm. Auroras pushing into Seattle, into Minneapolis, into Edinburgh and the Scottish Highlands. G1 is the floor. It is what forecasters expect if conditions cooperate. But the Bs, the orientation of that frozen magnetic field inside the arriving plasma, was still shifting between north and south as recently as yesterday, described by monitoring stations as weak and variable. Variable means unknown. Unknown in this context means the instruments are watching and the prediction models are running. And even so, no one can tell you with certainty what is about to happen in the next 6 hours. Think about that for a moment. Consider the city of Edinburgh, Scotland, a city of 500,000 people, set in stone in history at 55 degrees north latitude. On a normal Tuesday morning in May, those people are commuting, opening shops, sending children to school, accessing bank systems, using GPS navigation, the power lines that carry electricity into that city are long, and long power lines are antennas in the presence of geomagnetically induced currents. Consider the farmers of northern Manitoba, Canada, whose GPS-guided agricultural equipment operates on signals carried by satellites whose orbital drag increases measurably during geomagnetic storms as the upper atmosphere expands from solar heating. These are not abstract populations. These are people whose morning routines are entangled with infrastructure that has a known, documented, verified vulnerability to exactly the kind of event that is arriving right now as these words are being heard. This is not a hypothesis. This is documented in the geological and engineering record. On March 13, 1989, a coronal mass ejection struck Earth. The event resulted from 2 successive CMEs launched on March 10 and March 12, 1989, the first associated with an X4-5 solar flare, the second with an M7-3 flare. The second CME traveled to Earth in 31.5 hours at an estimated speed of 1,320 kilometers per second. T arrived at 1:27 Universal Time on March 13. 90 seconds later, the hydro power grid failed, not degraded, not flickered, failed. The entire province of Quebec, a geographic area twice the size of the state of Texas, went dark. 6 million people lost power in a blackout that lasted 9 hours. The Montreal Metro closed, Dorval Airport shut down. Schools and businesses went dark. People were trapped in elevators, in underground pedestrian tunnels, in office hours with no light, at the General Motors plant in Montreal, 8 hours of lost production at 44. 5 cars per hour amounted to 356 vehicles, a loss of approximately $6, 6 million from a single facility. A steel company lost $1. 5 million when the hot rolling mills went cold. What caused the Quebec grid to fail while other grids held was geology. The province sits on Precambrian igneous rock, which does not conduct electricity, well, forcing the geomagnetically induced currents into the path of least resistance hydro. As high-voltage transmission lines, the currents produced harmonic voltages that tripped the static VAR compensators one after another. With the last compensator gone, voltage on the Lagrange network dropped to 0.2 per unit. All 5 lines to Montreal tripped simultaneously through loss of synchronism. The loss of 9,450 megawatts of generation cascaded through the system in under 2 minutes. The floor shifted under an entire civilization's infrastructure. In less time than it takes to read this paragraph. That was a G5 equivalent event, the maximum level on the scale. This week's CME from AR4436 is not that. The forecasts from NOAA and the UK Met Office project G1, with the possibility of G1 to G2 conditions if the bees turns persistently southward. This is the critical distinction between a glancing blow and a direct strike, between a warning and a catastrophe. But here is what the data also shows. The 1989 event was caused by 2 successive CMEs, the first clearing the path for the second arriving faster and harder because the interplanetary medium ahead of it had already been swept. Scientists choose their language carefully here, and that careful language is itself the warning. Forecasters watching AR4436 are not watching one active region in isolation. They are watching 2 regions, AR4436 and AR4432, both developing unstable magnetic configurations, both capable of additional eruptions, both in a geometry where a second, more powerful CME could be launched into the wake of the first. The system is not inactive, it is accumulating. Consider what the January 2026 event demonstrated about what accumulation actually means in practice. On January 18, 2026, active region 4341 produced an X1.9 flare, the most powerful flare category the classification system recognizes, and launched a full halo CME. A halo, meaning the ejected plasma expanded in every direction from the solar disk as seen from Earth, indicating Earth-directed travel. The CME shock arrived at Earth on January 19, 2026, at 2:38 p.m. Eastern Time. What followed was the most severe solar radiation storm in more than 20 years. NOAA's GOES-19 satellite measured a surge of high-energy protons accelerating from the Sun at levels that breached the S4 threshold on NOAA's 5-level radiation storm scale severe. The agency's official statement was explicit. The event exceeded the intensity of the October 2003 Halloween solar storms, which had themselves been the benchmark for major space weather events for over 2 decades. In January, NOAA notified the FAA, NASA, FEMA, NERC, and other critical infrastructure operators globally. International Space Station crew were directed to shelter in the most heavily shielded modules, the American Destiny module and Russia's Zvezda. High-frequency communications were cut off completely in polar regions. Airlines rerouted polar flights, and simultaneously, a G for geomagnetic storm severe, the second highest category, was developing around the arriving plasma cloud. The magnetic energy at Earth reached nearly 20 times normal background level, confirmed on the record by Sean Dahl, space weather forecaster at NOAA's Space Weather Prediction Center. the infrastructure held, the protocols deployed, the preparation built over decades after the 1989 Quebec blackout was tested and, in January 2026, passed. But the question that remains the question that the data raises and refuses to answer is not whether the protocols will hold for a G for event accompanied by an S for radiation storm that has now been tested. Question is whether they will hold for an event larger than any infrastructure engineer has had the opportunity to actually test against real-world conditions. The Carrington Event of 1859 is the answer that question does not want. On September 1, 1859, British astronomer Richard Carrington was observing the sun through his telescope when he witnessed a bright white light erupt from a cluster of sunspots, the first recorded observation of a solar flare by a human being. The coronal mass ejection that followed traveled from the sun to Earth in just 17.6 hours, a transit time that speaks to a velocity so far beyond typical CME speeds that it stands alone in the historical record. The resulting geomagnetic storm, the most intense ever recorded by ground-based magnetometers, confirmed across observatories worldwide, produced auroras visible in the Caribbean, in Colombia, in the Sahara Desert. Telegraph operators in Europe and North America reported receiving electric shocks from their equipment. Some operators disconnected their batteries entirely and found they could still send and receive messages, powered entirely by the geomagnetically induced currents flooding through the wires from the planet itself. Telegraph offices caught fire. The technology of 1859, as primitive as it was, could not withstand the electromagnetic fury of what the sun delivered. A geomagnetic storm of that magnitude occurring today, striking a civilization whose entire operational architecture rests on high-voltage transmission lines, GPS satellites in low Earth orbit, fiber optic relay infrastructure, and interconnected financial systems, would not produce sparks in telegraph offices. Researchers at the National Academy of Sciences have estimated that a rare but powerful magnetic superstorm of Carrington intensity could cause continent-wide loss of electricity and damage to power grid infrastructure that could persist for months. The economic cost to the United States alone has been estimated at in excess of $1 trillion. The transformer system's most vulnerable extra-high voltage transformers that manage the bulk power flow across continents are custom-built components with replacement lead times of 1 to 2 years or more. The question is not whether a Carrington-class event will occur again. In 2019, researchers using Weibull distribution analysis estimated the probability of a Carrington-class storm striking Earth between 2018 and 2027 at between 0.46 and 1.88% per year, low probability, not zero probability, and solar cycle 25, the cycle that produced January 2026 ESS for event that produced the G5 superstorm of May 2024, and that is now driving AR4436 and AR4432 toward Earth's strike zone in May 2026, was originally forecast by NASA to be a below-average cycle. The official prediction, issued before the cycle began, was that solar cycle 25 would be weak. It was not weak. It has already delivered the strongest radiation storm in 23 years, the strongest geomagnetic storm in 2 decades, and is now delivering a glancing blow from a flare that NOAA classified as moderate. The question is not whether, the question is when, and here is where the connected systems matter, because this is not only a story about one sunspot region on one ordinary star in one unremarkable week of the calendar. The science that underpins modern space weather research is increasingly clear on a point that did not appear in the textbooks 2 decades ago. Extreme space weather events almost never result from a single CME. The 1859 Carrington event involved multiple eruptions. The March 1989 Quebec blackout was caused by 2 successive CMEs, the first clearing the path, the second striking with amplified force through the partially disturbed interplanetary medium. The G5 superstorm of May 2024, which produced aurora visible across the continental United States and as far south as Mexico, which is now the benchmark against which all current solar activity is measured, was produced by a cluster of X-class flares and multiple CMEs arriving in rapid succession. Scientists at NOAA and in peer-reviewed literature now use a term for this: CME-CME interaction. When 2 or more coronal mass ejections are launched in the same general direction within hours or days of each other, the leading edge of the first clears and compresses the interplanetary medium ahead, allowing the following ejection to travel faster, to arrive energized by the shock of the first. The combined magnetic structure of 2 interacting CMEs can produce geomagnetic storms far more extreme than either ejection would have caused in isolation. What the data from May 10th shows is a first ejection from AR4436 now arriving. What the data from May 11th shows is a second filament eruption from the southern hemisphere, a blob of solar material also under modeling analysis to determine whether any component is heading toward Earth, and what the data from both AR4436 and AR4432, both evolving, both magnetically unstable, both now rotating toward the Earth-facing position, shows is that the conditions for a CME-CME interaction scenario are not theoretical. They are geometrically available. There is another connected system that deserves the same gravity: the expanding thermosphere. When a geomagnetic storm energizes Earth's upper atmosphere, the thermosphere heats and expands outward into space. That expansion increases atmospheric drag on every satellite in low Earth orbit. The orbital decay rate accelerates. The hundreds of active satellites in low Earth orbit, communications satellites, weather satellites, the GPS constellation that underpins navigation systems on every continent, experience increased drag during sustained geomagnetic activity. In January 2026, NOAA's GOES-19 satellite recorded a thermosphere climate index reading of 16. 74 times 10 to the 10th watts elevated, though still well below the extreme hot values recorded during the October 1957 geomagnetic event. But during a sustained period of elevated solar activity like the one the instruments are currently recording, that number does not stay static. It climbs with each successive storm event, and it falls back slowly. The satellites affected by thermospheric expansion are not abstract infrastructure. They are the navigation systems used by emergency services in the cities of Northern Europe and North America. They are the weather monitoring platforms that provide the data models used to predict hurricanes before they make landfall. They are the communications infrastructure used by commercial aviation and maritime shipping, the same infrastructure that AR4436's M5-7 flare disrupted over the Atlantic Ocean when it fired. It's our 2 radio blackout on May 10th, 3 days ago. Consider the people living directly beneath the arc of this week's aurora lovel, the band of sky that will glow green and crimson tonight if the KP index reaches 5 as forecast. In Troms, Norway, a city of 78,000 people above the Arctic Circle that has learned to live under the northern lights as a fact of ordinary life, the aurora is not a spectacle. It is a reminder that the electromagnetic environment in which they live is different from the one further south. Power companies there are already monitoring grid operators in Scandinavia, where the bedrock geology shares characteristics with Quebec's Precambrian shield, are in what the industry calls a defensive posture. In northern Manitoba and Saskatchewan, Canada, the geology that made Quebec so vulnerable in 1989 extends across wide swaths of the Precambrian Canadian Shield. Farmers whose operations depend on GPS-guided planting equipment are, as of this morning, operating in an electromagnetic environment that is measurably, verifiably different from what it was 1 week ago. These are not neighbors far from here. These are neighbors whose names are simply not yet in the data. The sun operates on a scale that does not acknowledge human schedules or human budgets or the convenience of human attention cycles. Solar cycle 25 was supposed to be quiet. It was not. The cycle's activity peak was projected for mid-2025. Activity has not declined as predicted. AR4436, the region responsible for this week's events, sits on a sun whose 7 centimeter radio flux proxy for overall solar activity level was reading 126 solar flux units as of May 11, 2026. That number, maintained at elevated levels across multiple consecutive months, tells researchers that the solar surface is still dense with active magnetic structures. The sunspot number has not collapsed towards zero, the cycle has not ended, and the geometry of the coming weeks places AR4436 in an increasingly direct Earth-facing alignment as its rotation continues. Minutes are not hours, and in this context, that difference is everything. The fastest CMEs in the historical record have arrived at Earth in under 18 hours from their moment of launch. The Carrington Event of 1859 arrived in 17.6 hours. A camelanche from a fully Earth-facing AR4436 at X-class intensity could, under the right conditions, arrive at Earth before monitoring systems complete their first full modeling cycle. The ACE and Discover spacecraft positioned at the L1 Lagrange point approximately 1.5 million kilometers from Earth upstream in the solar wind provide roughly 15 to 60 minutes of advance warning between first detection of an incoming CME shock and its arrival at the magnetosphere, 15 minutes. In 15 minutes, grid operators must make decisions about whether to manually shed load, to isolate vulnerable transformer banks, to reroute power flows across the network. In 15 minutes, aviation authorities must decide whether to divert polar route flights away from the enhanced radiation environment at altitude. In 15 minutes, satellite operators must determine whether to put sensitive instruments into safe mode. The monitoring is in place, the detection is possible, but true prediction of the magnetic field orientation inside the arriving plasma cloud, the B's value that determines everything, is not yet, not with the instruments and models that exist today. This is not a hypothesis. This is documented in the engineering record of every major space weather event since 1989. What happened in the 9 hours of darkness over Quebec on March 13, 1989, happened because the geomagnetically induced currents followed the path of least resistance through the bedrock geology of the Canadian Shield and into the high-voltage transmission lines of hydro. The circuit breakers tripped, the static VAR compensators failed in sequence, the 5 transmission lines to Montreal tripped simultaneously, the 9450 megawatts of lost generation caused a frequency drop that cascaded through the entire provincial network in under 2 minutes. 6 million people, from Montreal to the far north, lost power in the early hours of the morning in March. They woke to cold houses. They found the metro closed, the airport dark, the schools empty. The blackout lasted 9 hours because 9 hours was how long it took to restore sequence to a system that had lost it all at once. A Carrington-class event would not produce a 9-hour blackout. It would produce something that the National Academy of Sciences and NOAA researchers have described as a long-duration event, a blackout measured not in hours but in months, driven by the loss of extra high-voltage transformers that cannot be replaced from a warehouse because they do not sit in warehouses. They are manufactured to specification, one at a time, with lead times of 1 to 2 years. This is not speculation. This is documented in the official record, and yet here is what must also be stated with the same precision. The systems built since 1989 are not the systems that failed in 1989. Hydro. Spent $2 billion over 6 years after the blackout upgrading its grid. NERC, the North American Electric Reliability Corporation, has issued binding reliability standards requiring utility companies to develop operating procedures and assess their systems for geomagnetic storm vulnerability. The USGS operates 14 ground-based magnetic observatories continuously across the United States and its territories, some of which have run uninterrupted for over 100 years. The FAA, NASA, FEMA, and major grid operators were all notified in January 2026 when the S for radiation storm arrived and the protocols held, the ISS crew sheltered, the polar flights rerouted. The infrastructure survived. Scientific honesty requires acknowledging this. Scientific honesty also requires acknowledging that the event that actually tests the system to its breaking point has not yet arrived in this solar cycle. It arrived in 1859, before the system existed. It arrived in 1989, when the system was young and unprepared. It has not arrived since, though it came strikingly close in July 2012, when a Carrington-class CME erupted from the Sun and traveled through the exact position in space that Earth had occupied just 9 days earlier. 9 days. Had the timing been different by 9 days, the CME that passed through empty space in July 2012 would have struck Earth directly. NOAA researchers who analyzed the event afterward estimated it would have produced a geomagnetic storm comparable in magnitude to the Carrington Event itself. Earth did not know it had been missed. The instruments recorded it. The papers were published. The public did not notice because the target had already moved on. AR4436 is rotating toward Earth's strike zone. The CME it launched on May 10th is arriving at this planet's magnetosphere today, on May 13, 2026, in a glancing blow that forecasters currently expect to produce G1 conditions auroras over Scotland, over the northern United States, over cities whose power grids are better prepared than they were in 1989, and less prepared than they would need to be for something larger. The B's value of the arriving plasma is still variable. The orientation is still unknown, and behind this arriving wave, 2 active sunspot regions with unstable magnetic configurations continue their slow rotation toward the most dangerous position in the solar geometry. The system is not inactive, it is accumulating. The question is not whether a larger event will eventually arrive from this star. The geological record denies cores and tree rings and carbon-14 measurements from the years 774 and 775 CE, when an event 20 times the normal variation of solar activity was preserved in the biochemistry of living wood answers that question with the same finality with which the bedrock of Quebec answers questions about what happens when the currents have nowhere else to go. This has already happened once. The record of it is still preserved in the rock, and the Sun, which has been performing this cycle of charge and release for 4-6 billion years without regard for the civilizations that have briefly arranged themselves across the surface of the third planet, does not distinguish between a rehearsal and the event itself. The light that left sunspot region AR4436 on May 10, 2026, took 8 minutes to reach Earth. The plasma that followed took 3 days. It is here now. The next time AR4436 fires, from the position it is rotating into, the warning window will be measured in minutes. The infrastructure will respond, as it has been designed to respond. And the B's component of whatever arrives next will not be known until it is approximately 15 minutes from the magnetosphere of this planet, this fragile, electrically dependent, interconnected civilization built on the surface of a world whose magnetic shield was already old beyond human comprehension before the first wire was ever strung between 2 cities that needed to share a current.